Bismillahirrahmanirrahim dan Assalamualaikum. A very good afternoon and welcome to INBIOSIS Webinar Lecture Series 2 2021. I am Zeti, Azura Mohamed Hussein, and I am your moderator for today. So I hope the video has provided you with some of our background. So for those who are interested to collaborate with us, you are most welcome to do so. And please feel free to browse INBIOSIS website and social media for the latest updates and info. Alhamdulillah, today Allah has granted us with good health and time to attend our second INBIOSIS 2021 webinar. And inshallah, there are many more to come. And I hope all of you will join it again in the future. For your information, INBIOSIS webinar series is established to provide a knowledge and research experience sharing platform to ensure we are still connected with each other and stay motivated in our research despite this sudden pandemic. So the session will take about 45 minutes of lecture and 15 minutes of question and answer session. So the participant can post the questions in the chat box and I will read them during the Q&A session. Before the seminar ends, I would like to invite all participants to switch on the camera for a photography session. Please stay tuned until the end of the session to fill in the attendance form for e-certificate and e-spell UKM credit. So today we are very grateful to have with us our honorable speaker of the day, Professor Dr. Suraya Abdul Rashid from Universiti Putra, Malaysia. So she is the most suitable person that can help us and that can share with us her experience how to bring your research output to the commercialization level. So please allow me to share with you Prof. Suraya's CV. So Prof. Suraya Abdul Rashid is a professor of chemical engineering specializing in nanotechnology at the Department of Chemical and Environmental Engineering, Faculty of Engineering, Universiti Putra, Malaysia. Currently, she is the head of the Materials and Processing Laboratory, Institute of Advanced Technology, known as ITMA UPM. Her research interests revolve around synthesis, processing, and characterization of various nanomaterials, namely carbon nanostructures. Her research also extended into the use of nanomaterials for a variety of applications, such as high-performance nanocomposites, that is polymers and concrete, supercapacitors, nanosensors, and more recently, nanoagriculture. So this is one of the reasons why I am keen to have her with us to share her work in agriculture. She is also a chartered engineer under the Institution of Chemical Engineers and also a nanotechnologist under the Malaysia Board of Technologies. She is also a technical director for a startup company that commercializes her research product, which is a photosynthesis enhancer for plants. She has a broad network and experience with industries locally and internationally alike. So without further ado, I would like to welcome Prof. Suraya to share her take on research innovation. The floor is yours, Prof. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum and very good afternoon, everyone. Can you hear me? Dr. Zeti? I hope everyone can hear me. Okay, all right. Thank you so much. Thank you so much, Dr. Zeti Azura, the director of INBIOSIS, for inviting me to give a lecture for the INBIOSIS webinar series number 2 this year. Congratulations for this initiative INBIOSIS. It's a very good initiative and I hope it will bridge more connections between different institutes for us to work together, inshallah. So I would like to share my screen and turn off my video for more stability. Okay, so the title of my presentation today is Research Innovations, Evolution from Technology Push to Market Pull. So I thank you, Dr. Zeti, for inviting me. We became acquainted over plants, which I think is really beautiful. And because Dr. Zeti came across a research product of mine, and today I would like to share with you my experience of how my research evolved from technology push to market pull. Okay, so for this talk, there will be several subtopics. Initially, I want to share with you and just make sure that you have some basic understanding about the nanoscale and nanomaterials. And then I will share about the evolution of my research in nanotechnology, beginning from when I came back from my PhD back in 2004 until today. And then I will focus more on a certain nanomaterial, which is called carbon dots, and see their various applications. And I will focus more on a certain application related to plants. I would also like to share the role of UPM's Putra Science Park and Innovation Hub, in assisting researchers to bring their products from lab to market. And then I want to share with you some tips about how you, as maybe you're a researcher or a young researcher, how you can, tips on how to innovate your research product. Okay, very briefly, brief introduction about ITMA, which is Institute of Advanced Technology in UPM. Our director is Professor Dr. Mohamed Hamidun, and we have three main labs there: Material Synthesis and Characterization Lab, headed by Associate Professor Dr. Azura, and myself. I am heading the Materials Processing and Technology Laboratory, and Dr. Suhaidi, Associate Professor Dr. Suhaidi, is heading the Functional Devices Laboratory. We have our Deputy Director, Professor Dr. Ahmad Zahrin. So all of us come from a multidisciplinary background, from engineering to science, right? And ITMA brings together the science and technology for us to develop innovations. Okay, we have 44 personnel in ITMA. The management, all the management is consists of researchers. We have permanent staff there. Our research officers, our science officers, they are permanently there. Okay, so we have postdocs, research fellows, and contract staff as well. And the research groups focuses on nanotechnology, and we have various research groups in ITMA. We have nanomaterials, nanomaterials processing, we have sensor technology, electron devices, functional and structural materials, and a relatively new research area. If you have heard of metal organic frameworks, we have a research group dedicated to that as well. Okay, so how small is the nanoscale? Nanoscale is extremely small, and people have because we can't see it. Some people have difficulty imagining how small is small. So if you could imagine our Earth, right? Our Earth, if our Earth has a diameter of 1 meter, then 1 nanometer is equivalent to the size of a marble. Okay, so this is the huge difference in size when we are talking about the nanoscale. All right, and so when we talk about the nanoscale, usually we are talking about nanomaterials and how nanomaterials are being used in different applications. The nanomaterials could be organic nanomaterials, could be non-inorganic nanomaterials. Organic ones could be made out of carbon, and inorganic ones, semiconductors and metals. And another unique thing about nanomaterials is their size. and their morphology, their shape. You could have like a fullerene type structure, you could have a tubular type structure, sheet-like structure, wires, and even like really, really tiny ones. These are the images you see here are not to scale, but the carbon dots that I will be talking more on today is very, very small, around less than 5 nanometers in size. And why it's so special about nanomaterials? At the nanoscale level, materials no longer behave like the bulk material, but often have enhanced chemical and physical properties. Okay, so when we're talking about carbon materials, carbon-based nanomaterials, if you have a carbon sheet, like graphene, for example, its properties will be very different from, say, you have very small fragments of carbon, like carbon dots. Okay, so the reason people are interested in nanomaterials are because they could be more stronger, the same size, but the same material, but more stronger. For example, carbon nanotubes are considered stronger than steel. Under certain conditions, they could be more reactive, they could be more resistant, they could be more accessible. And this is why scientists are very much interested in using nanomaterials. Okay, so I want to share with you the evolution of my research work. I came back from PhD in 2004. I did my PhD in Imperial College London in the area of nanotechnology as well, where we use atomic force microscopy to characterize polymer films. Right. So when I came back, I found myself being involved with a top-down project at that time to produce high performance nanocomposite. Okay, and this was not just any nanocomposite. It was using carbon nanotube hybrid fiber. Okay, and the application for this is, as the name suggests, high performance nanocomposite. You could use it at that time. We wanted to use it to make CNG tanks, compressed natural gas tanks, which had to be very strong yet light. All right. So and then other applications were body parts of maybe automotive body parts, maybe sports equipment, things like that. Things where more for the structural application. And this was back in 2004. Carbon nanotubes was very, very popular at that time, and a lot of effort, energy was put into studying carbon nanotubes for nanocomposites. Right? We spent 10 years. 10 years was spent in this area, and of course it was very, very really, really high tech, very good findings that was carried out, very good quality research that was carried out. But if you talk about commercialization, then it began to seem a bit more difficult. Right, a bit more difficult, because when we produce nanomaterials, it is at lab scale process. Yes, we focus on scalable processes. For example, if you're familiar with chemical vapor deposition, then it is technically a scalable process. Okay, we can scale it up to larger scale to produce more. But at that time when you start, you only produce grams of this material in batch quantities, right? And so it became apparent that it was difficult to commercialize. And later on, I will share more about difficulty in commercializing technology when you have something so good, but it is difficult to push to the market. Because our industry at that time, there was no takers basically for the technology. There was no takers for the technology. People didn't really want to invest in something they weren't so familiar with, right? So it was just very difficult to push. And this is an example of technology push to the market, okay? And thinking about continuing the research, there came a time where I decided no longer to pursue synthesis of carbon nanotubes, because personally I felt that it would be difficult to the application, the nanocomposite application was a bit difficult for me to pursue, because I need to scale up from lab to a larger pilot scale facility, for example, and that was very expensive and quite challenging. So I began to, the research evolved to still carbon-based nanomaterials, but we began to look at two-dimensional nanomaterials now, such as the graphene oxide. And what is graphene oxide used for? Mostly used for the applications that we were looking at, that I was personally interested in, was for gas sensors. And why did I decide to go this route? I wanted to work with something on a smaller scale. And the gas sensor application, you do not need a lot of material, right? You do not need a lot of material. Therefore, it seemed to be a lot more feasible, in my opinion, to commercialize. And at that time, I also had the opportunity to work in industry. I did an industrial attachment with a company in Senawang. They had a business in biodiesel, but they had a small division in nanotechnology, and I had the opportunity to work on this material at that company. And we looked at not only gas sensors, but also supercapacitors. And there were research students, PhD students working in this area as well. And then, discovering the unique properties of graphene oxide, we found different applications, and we found that it could be, and we look more into the sustainability aspect. And at that time, 2017, the conversion of carbon dioxide was quite a hot topic. And so we tried to study this area, carbon quantum dots in titanium and nanocomposite catalyst for carbon dioxide conversion. Again, if you look at is it possible to commercialize or not, it's very difficult indeed. So but never mind, at least we had I was focusing more on how to make my expert. I'm a chemical engineer, so I was focusing on more how to make nanomaterials at a larger scale. And we found, so from graphene oxide, we found graphene quantum dots and eventually carbon quantum dots. They are similar, slightly different. So from now on, I will refer to this material as carbon quantum dots. And these carbon quantum dots, they are very, very fascinating. They are the smallest. They are zero-dimensional nanomaterials, and they have very fascinating properties. They are photoluminescent. When they are photoluminescent, the application is more for sensors, for photovoltaics. But now I suddenly found a potentially new application for carbon quantum dots. Okay. Oh, sorry, I didn't press. Okay. Can you see my screen? Suddenly my screen is not responding. Yes, thank you, Aimee. Thank you, Aimee. Okay, so I I think I will skip this. This is just to illustrate to you the carbon nanotube, high performance nanocomposite that I spoke of just now. These are the applications. And I want to straight away go to the carbon quantum dots. CQD have unique electrical and optical properties which render them photoluminescent. This means that if we shine light onto them, then you can see they will emit some color. Okay, and in this example, the screen, you can see bluish color under UV light. And although semiconductor quantum dots are not new, the discovery of CQD is relatively recent, around 16 years ago in 2004. And a lot of work has been carried out to synthesize and characterize CQD because different synthesis approaches yield different sizes with different surface functional groups and different photoluminescent properties. And this is the desirable photoluminescent properties of CQD. The photoluminescent is under long excitation wavelengths, they have tunable emission wavelengths, they have up conversion luminescence, and they have visually perceptible color changes. Okay, so I was more interested in the processing of these nanomaterials. You know, we want to develop processes which are scalable. Only when they are scalable, then it has potential for commercialization. And so the preparation of CQD, there's two ways of preparing material. One is the bottom-up approach and one is the top-down approach. Bottom-up is when you begin with atoms and you make clusters and you make nanostructures, and usually there's a reaction involved. Top-down is when you use bulk material and you cut it up. It goes under grinding, milling, processing until you obtain your nanostructures. Okay, and bottom-up, usually you have hydrothermal synthesis approaches where you have heating is involved. And then for the top down, the conventional way to make carbon dots is electrochemical exfoliation or chemical oxidation. Chemical oxidation is the most popular way to make quantum dots. However, there is disadvantage in this approach whereby it involves harsh chemicals and oxidants, and therefore that you need, if you are talking about scaling up the process, you really need to be careful because you are dealing with potentially dangerous chemicals. Okay. And the starting material is also, there are various starting materials. If you choose the top-down method, there are various starting materials. In 2013, some of the earlier work was using coal as using chemical oxidation, and then waste biomass, and then natural carbon materials. And in 2015, we made our own using graphite nanofiber. And this is when I discovered the difficulty in using chemical oxidation process. The chemicals are nasty in the sense that they are very, very strong acids. And when at the end of the process you have acidic conditions, you really need to neutralize. And neutralization produces a lot of impurities, a lot of salts. And when you're talking about very tiny structures, you have to be careful, and you need to use dialysis methods, which is expensive and just quite quite challenging. Okay, and so I thought that in order the way forward to produce on a larger scale would be to go to find an alternative, to find an acid-free process, and that is what we try to pursue. And like I mentioned just now, these are the conventional way is of top-down process is chemical oxidation. Now we tried hydrothermal extraction. Okay. And the advantage of hydrothermal extraction is that it is acid-free process, it is very simple or very facile, it has potential to be scalable, and more importantly, it is economical, okay? Because you do not need complicated equipments to do this process. And at that time, we filed a patent. It's still patent pending, but we filed a patent to produce carbon dots. Okay, and if you, I like to share a little bit about the characterization, because these are so tiny. You need to, in order to characterize or to see nanomaterials, you need to use certain equipments, and these images show the high resolution transmission electron microscope, and you can see that this solution contains the carbon dots. It is photoluminescent. You can do profile of the structures. They are typically around 3 nanometers. You can see the scale there. They are typically around 3 nanometers. And this is another image of the structure as well. And then an important thing about photoluminescent material is that you can check, you can measure the photoluminescence spectroscopy. Okay, and here it shows the when we use a hydrothermal process, you can see that the material shows photoluminescence with this emission here. And then however, without the hydrothermal process, there is no photoluminescence. Okay, and you can study this further. You can change the excitation wavelength, and you can study their behavior, and you can characterize using FTIR to see their functional groups. You can use X-ray photoelectron spectroscopy to determine what are the functional groups on the surface of this material. Okay, and we did a lot of this. You can, because they are carbon, you can use Raman spectroscopy to determine to characterize them further and to see their behavior. To see their photoluminescent behavior. All right, so the potential applications of carbon quantum dots make use of both their electrical and optical properties. Okay, they are photoluminescent, means that they have unique electrical properties, and they have unique optical properties. And we decided to investigate this this further, and we applied for grants, and of course a lot of research, a lot of money was being put into all of these applications. For example, for the we made conducting polymer carbon dot electrodes for supercapacitor application. Carbon dots was used for photovoltaics, where we studied how carbon dots can improve the performance of dye-sensitized solar cells. We looked at more sensors using their optical properties. For example, biosensor using carbon dot conjugated enzymes, using sensors using surface plasmon resonance. So, you know, all of these are ongoing research. Whether or not they can be commercialized is a different story altogether. Okay, you can push this technology. Of course, photovoltaics is far from commercialization still. The other sensors, I think, because I'm not a sensor person, maybe you have more idea about how close or how easy is it to commercialize. I felt that, you know, my experience with technology push, I was scared. So it was more like to do research for academic purposes. Of course, you can produce so many good work. You can publish in very high impact factor journals. Can you commercialize? That is a completely different situation altogether. Okay. And if you recall, just earlier, I mentioned about using carbon quantum dots as photocatalysts for carbon dioxide conversion. And you know, it was my personal quest, or my personal desire to try to commercialize. I had already spent so many years doing research. I knew what that was. I knew about research, how to do good research, how to do impactful research. But how do we bring this research product to market? How? right? And so I felt that then we had to find a niche area. And because I had so much knowledge about the material that we had developed, I had so much knowledge about the process. It was easy, it was economical, it was safe, right? We had a material which was had so much potential. So I decided that I had to find a niche area. And this is when I thought, if the carbon quantum dots, because of their unique photoluminescent properties and because they can be used as photocatalysts, perhaps they can be used for photosynthesis. And because I knew about their properties, they were safe, they were biocompatible, and they were economical to make, it started to get, the idea started to get a lot more interesting. And so, because also UPM, Universiti Putra Malaysia, we focus on agriculture-based research, right? And it was a very interesting niche area to study. I did a quick search to see what people had developed in this area, and there was not much, to be really honest. Yes, people use other types of nanomaterials to see their impact on plants. That's not new, right? That's not new. A lot of people have done that. However, to actually apply nanomaterials specifically for photosynthesis, it was relatively new. People were using other types of carbon nanomaterials, such as carbon nanotubes, right? And they saw improvement. So I thought, if um, if carbon nanotubes was useful for plants, then carbon dots must be even more useful. And it must have impact on photosynthesis. And to test this further, it was outside my expertise. And so I had to work with people who are experts in this area. And I approached researchers from Faculty of Agriculture, and I said, I have this idea. Can you help me? This is not my expertise. And they said, yes, let's try. And this is when it began really interesting. And we tested the hypothesis in UPM using, our greenhouse facilities and so on. And we found that, yes, the hypothesis that carbon dots could be used to improve the photosynthesis of plants, the photosynthetic rate of plants, right? So I did my own study at home. It wasn't difficult to set up the hydroponic system. So you can see that at day 26, the treated sample, this is very basic, right? Very basic research. The more the controlled research was being carried out in UPM. Right, but there was promise. And why was carbon dots? Why could it have impact on photosynthesis? Because it has similar properties to chlorophyll, in that it will react to the UV light and create an emission. These unique electrical and optical properties assist in the electron transfer mechanism during photosynthesis. And at this time, our paper is currently, to explain this mechanism, is currently under review. Okay. And we tried to measure the photosynthesis rate of various crops. We tried paddy, we tried choy-sam, and it was unique. It was interesting to see unprecedented increase in photosynthesis, whereby for paddy we saw an improvement of 55%. For choy-sam or sawi we saw an improvement of 84%. You know, because sawi is made mainly out of leaves. So depending on the different types of leaves, you get these different increase in photosynthesis rate. And we can talk more about photosynthesis, you know, why photosynthesis is an inefficient process. However, some plants have evolved to improve their photosynthetic capabilities, you know. So this perhaps for a different time, because I want to share with you more about the commercial side. This shows this LICOR portable photosynthesis system gives us light response data and carbon dioxide response data, right? And the data extracted from the light response curve showed that this was done on chili. Carbon dot treated chili assimilated 62% more carbon dioxide molecules for each photon of molecule absorbed. And then for the carbon dot treated chili required less light to achieve optimum photosynthetic rate. The carbon dot treated chili had 33% higher photosynthetic capacity than the control. Okay, and so this was a data extracted from the light response curve, and from the carbon dioxide response curve, it shed more insight into Rubisco catalytic activity, into electron transport rate, into stomatal conductance values, as well as water use efficiency. The water use efficiency is unprecedented and is very interesting. However, we need to study this further, all right? There's so many things to study. People say, Suraya, did you check this? Suraya, did you check that? Have you checked this? Have you checked that? No, I haven't checked because I do, you know, to check, to do all these studies requires grants, requires students, requires, so I am doing the best that I can, all right? And this is when UPM, I love UPM. UPM Putra Science Park is our commercialization arm. And these following few slides are taken from Dr. Wan Nur Hayati. So thank you, Dr. Wan, for sharing with me. Putra Science Park is, I would say, has really enabled me to explore the commercialization of carbon dots for photosynthesis enhancement. All right, and so in PSP, PSP is involved with technology transfer activities, moving potential technologies and inventions from the laboratory to the marketplace. Okay, and this is the current organization chart. Our director is Professor Dr. Mohamed Hebejo, and our Deputy Vice Chancellor of Research and Innovation is Professor Dr. Zulkifli Idros. Under PSP, we have two main divisions. Associate Professor Dr. Wan Nur Hayati is the Deputy Director for Innovation, Promotion and Commercialization Division. And we have Associate Professor Dr. Zahira, who is the Deputy Director for Intellectual Property Division. And when you want to commercialize your product, your research, your technology, you have to work very closely with these two divisions. Okay, and you really, because UPM will only allow usually products which have patent or intellectual property, can only be commercialized. Okay, so I work closely with them. And not only that, UPM has a very unique program. UPM has what we call the market validation hub, the innovation hub. Okay, so what this is that researchers who have potential product to commercialize can approach InnoHub and propose their product to to obtain market validation grant. Okay, and there is a purpose why UPM does this. Okay, there is a purpose because conventional approach of commercialization is really people not really focusing in the valley of death. All right, and what InnoHub allows is for researchers to check the hypothesis, to check that they get the hypothesis that people who wants their product, the market who wants their product really wants their product. And so, InnoHub champions UPM's R&D intellectual properties to market by training, nurturing young unipreneurs to fill the commercialization gap. And so, in 2000, I would say 2017, this is when me and a project manager, the unipreneur, approached InnoHub and said, we have this this idea, and the InnoHub was extremely UPM was extremely cooperative. We obtained a we obtained a market validation grant, and that market validation grant was extremely valuable in my case, okay, where I wanted to push carbon dots to as a photosynthesis enhancer. So we checked, do people really want this, right? So at that time, the idea was to push for agriculture, was to push to farmers. However, it was not as easy as initially expected, because farmers, what they want is, show me how much improvement in yield will I get if I use your product, this photosynthesis enhancer? How much yield would I get? So we didn't have sufficient data, and people want to say, do you have field data? No, we don't have field data yet. We only have greenhouse data, but greenhouse data is not enough. And so they wanted like field data. In order to carry out field data, you need to scale up the process to meet the volume needed for field data application. All right. So at that time, we hadn't reached there yet. Right. So these are all the challenges that we face when we think, oh, I have a product that has potential to be commercialized. Right. So at that time, 2017, I was naive, but it's really a learning process, a long learning process, and it can only happen if you want to innovate. If you feel it's not easy at all. Okay, it is not easy at all. So, but it is rewarding if you are patient and willing to try. Okay, and so and then MCO happened in 2020. The first MCO happened, and at that time we were yes, we could sell. People because I already had this product, so I sold to my neighbors. I asked my neighbors, would you like to try this photosynthesis enhancer? They said, okay, let's try. And when they tried, they said, Suraya, it's so good. It helped my plants do this and this. It helped my plants to flower. It helped my plants to increase leaves. It make my plants look more beautiful. And so I thought, okay, so it's not just me who thinks so. Other people think so as well. And at that time, we were selling maybe one bottle a week, or maybe one bottle a month. Because I also had a mental block at that time. I thought that I cannot do this alone. All right, I cannot do this. I need somebody to assist me. But after I talked to, in InnoHub, there's our mentors there, and they give me encouragement, and I really I felt because at that time I no longer had a project manager. I no longer had a project manager, so I had to do something. So I pivoted. What does pivot mean? Pivot means that to pivot from your original idea to something else. So this is when I pivoted during MCO of 2020. I pivoted. I said, okay, let's focus on the horticulture market. Let's focus on the horticulture market, because there's people during MCO, people were interested to collect plants. More and more people were collecting plants because people were at home. People wanted a safe, to feel feel happy with their plants, and there seemed to be a pull from the market. And this is when I pivoted, and so what was involved was I redesigned the packaging with help of other people. We repackaged this into what it looks like today. You can see this slide. This was before and after, and then you can really see that the before is what we designed, which was not very nice compared to what the professional designer designed, and it was a lot more nicer. And all these things come into play where you have nicer packaging and people willing to try Harvard's photosynthesis enhancer. It helps revive and rejuvenate dormant plants. It helps to stabilize transplanted plants. It helps with faster cell regeneration and plant recuperation from injury. Stronger and healthier leaves help plants to be more resistant and resilient to pest infestation and disease. All of this was based on greenhouse data. Okay, and not only that, it had even more potential, because if you look at harnessing light for a sustainable world, this is where I'm pushing this. This is more of a technology push. If we want to change from fossil-based economy to circular bio-based economy, then we can do this. We can heal the world through energy from the sun. This is like really, really incredible. And I will talk more if I have time, talk more on that. Okay. And, we can harness light. Sorry, if we use this photosynthesis enhancer, it has potential to address SDG goal number 2, because from zero hunger, we can make agriculture more efficient. Okay, so there will be more food for people. Good health and well-being. This is related to pollution, which I will mention after this. Clean water and sanitation. If we are able to reduce carbon dioxide, because photosynthesis is a process of converting carbon dioxide into sugar and oxygen, right? So if we are able to reduce carbon dioxide levels, which is a greenhouse gas, we will be able to reduce acid rain. Okay, and this is also related to another SDG later, affordable and clean energy. We saw how carbon dots can be used in photovoltaics. We can sustainable cities and communities. There is potential for cities to develop their own carbon sinks through parks, through green areas in the cities, right? Which can improve, which is related to number 3 as well, when you reduce greenhouse gases. Okay, and 6 and 14 are related as well, where you and also carbon dots are able to be used as sensors, for example, and you can monitor the clean water and sanitation, the acid rain. Less acid rain can protect life below water. More efficient agriculture reduces the need to cut down our forests, right? So if we are able to maintain or protect our forests, then we can protect our life on land. So this is it's not just about making your plants beautiful. There's a huge impact on SDG as well. And so this is my final slide, tips for researchers to innovate. I would say be willing to work outside your comfort zone. Take the path less traveled, even if it means going against the grain. At the time when I studied graphene, right? When I studied graphene, everyone was looking at large area graphene. Not many people were looking at tiny carbon fragments. Not many people were looking at that, but I felt I felt the desire to go small. I felt the desire to go small. So photoluminescence of carbon dots really fascinated me. So I thought it's okay. Other people can study that. I will study what my heart desires. Okay, and then be creative and innovative in solving problems and finding solutions. Technology cannot be commercialized unless it is scalable and has an economical edge. So if you are looking for commercialization to commercialize your product, please, you need to address scalability and make sure that economical. Because if we were to venture carbon dots were to be applied for agriculture, it has to be economical. Otherwise, it just wouldn't be possible. And we used the starting material we used was agro waste as well. So that was something good as well. Identify a niche area and subsequent niche market. Focus on market pull, not technology push. So in this certain example, I saw that there was a market pull and took advantage of that to move forward. Of course, for all the other applications that I mentioned just now related to the SDGs, of course, there will be technology push, and each of those areas will have their own challenges. Okay, so you have to, but at least we know that there is this untapped niche market that we were able to venture into. And another one is work with a multidisciplinary research team. Okay, because for example, I do not know. I'm a chemical engineer. I know about what I know is how to make nanomaterials. I know that. Do I know about photosynthesis? I didn't. So I had to work with those who did. Right? And so it is impossible for us to know everything. So we need to leverage on other people's expertise. And I would like to, before I end, because I'm already running out of time, I'd like to acknowledge my past and present postgraduate students. My current postdoc, Dr. Tan Tong Ling, Itma, of course, my co-researchers, of course, from Faculty of Engineering, Faculty of Science, and Faculty of Agriculture, research grant providers, as well as InnoHub, Putra Science Park. Without InnoHub, no way, no way would I be able to, go this certain path that we went through. And sometimes, don't be discouraged, because when you're in a dark place, you think you've been buried, but actually you have been planted, and you can come out stronger, inshallah. That is all from me. Over to you, Dr. Zeti Azura.
Okay, thank you, Prof. Suraya, for a very enthusiastic presentation. So I can feel the vibes and positive energy in this. Okay, so I think, right, shall I start? We have a couple of questions here, but shall I start first? Okay, first of all, I would like to know how many grants have you worked on before you start venturing on this part of your project?
Dr. Zeti, do you mean from 2004, from when I first started, or
no, I mean that is directly related with this, yes, CQD. Because sometimes, because we are doing our proposal, some of the aspect requires the commercialization output and so on. But in some cases, in some field, there is impossible to go towards that line, right? But in your case, can you share with us?
Yes. So specifically for this, I would say 2 research grants. Two research grants, I would say, and then 1 market validation grant. So the research grant was from UPM's internal grant, which is Grant Putra Berimpak. And then the amount was around, in the initial one was around 200,000 ringgit, I think. And then we had another one which was 500,000 ringgit. So that was for the research grant. And then for the market validation, it was around close to 100, but slightly less than 100. I cannot remember exactly. So 3 altogether, Dr. Zeti.
Okay, thank you, Prof. So I will read questions from the participant. The first one is from our FB Live. The question is from Dr. Go. CQD needs to be sprayed evenly on the leafy plants. Any environmental implication of nanodot application in agriculture?
Okay, so the carbon dots are actually derived from agro waste, from biochar, and the processing does not involve any harsh chemicals. So the final product that you obtain is is not acidic or anything, and the concentration that is being applied onto your plants is extremely low. So it's very low and yet sufficiently effective to enhance photosynthesis. And we did toxicity tests as well and saw that I would say that if it's safe for you to eat satay, which contains a lot of carbon, or barbecue, you are consuming more carbon than the plants which are being sprayed with the carbon dots.
All right, okay, thank you. So the next one from Dr. Nisha. Prof. Suraya, thank you so much for highly informative presentation. I hope to use harvest on my balcony grown plants soon.
Yeah, yes, please. Yeah,
Few
welcome.
questions for you.
Yeah.
Okay, one, please comment on mesoporous nanoparticles for agricultural use.
Mesoporous?
Yeah.
Okay.
So maybe I let you answer the first question first before I read the second one. All right.
Mesoporous materials. What would it be used for? I think it depends. But for example, in agriculture, there is practice of putting in biochar to the agriculture area, and this improves the soil. So it depends on why are you using the mesoporous material. What is its application? Sorry, does that answer the question?
I hope she will respond to it later.
Okay.
Okay.
All right.
The second question, which technique is the most feasible, bottom up or top down, for upscaling terms of efficiency?
It depends. Both would be feasible. Both would be possible. I chose the top-down process because I wanted to. I'm not a chemist. I wanted to stay away from chemistry, stay away from reactions in making the carbon dots. So I chose the top down because I was more familiar with top down anyway. Top down process for the material I was working on was a more conventional method, so I was more familiar. Doesn't mean to say that you cannot use bottom up. Does not mean that at all. Of course, if you found a suitable process, bottom up processes are also scalable. Hydrothermal processes are also scalable. So it depends.
Okay. Right. My question here, Prof. So when you use a bottom up, there will be a lot of impurities and waste, right? Okay. So how do you usually treat those impurities and waste?
Okay. So when you're dealing with, is this bottom up or top down? I think the question was bottom up.
But this one is my question.
Right. Okay.
So how do you usually remove the impurities and waste?
Yeah. So the typical way would be to use some sort of separation process. If you are dealing with materials which are really small, like carbon dots, they are tiny, they are 3 nanometers, then you need to be careful, and you need to the most common way would be by centrifugation, right? If you have a lot of salts as impurities, then you need to do dialysis. Okay. Our process we can say for the application of carbon dot for photosynthesis enhancer, this is not an issue. We can skip the dialysis. The dialysis is a very expensive step.
Okay. All right. Thank you. So the next question from Dr. Aizat. Thanks, Prof, for such an interesting talk.
Thank you.
I have two questions. Number one, what is harvest made from?
Okay, so the active ingredient in Havas is carbon dots. They are photoluminescent, and when you apply them as a foliar spray, they will be able to penetrate the leaves, interact with the chloroplast, which contains the chlorophyll, and will assist in the electron transfer mechanism of photosynthesis. That is generally how it's being done. If you wanted to ask me more about electron transfer mechanism, we are still studying that.
All right. So the second one, if I'm not mistaken, one of the benefits of using harvest is to reduce pest infestation. What kind of pest that it can target?
Okay, so this one was specifically tested on chili plants. If you are familiar with chili, chili attracts a lot of pests. So if from our greenhouse studies, we saw that the carbon dot treated chili and the untreated chili, the carbon dot treated chili was a lot more healthier, okay, compared to the compared to the control chili with no treatment at all. And we believe this is because when you apply the photosynthesis enhancer, what it does is it helps to make the leaf a lot more stronger and more resistant to various pests. So the pest that we're talking about is the common pests for chili plants. They attract so many pests. Sorry, I forgot the name of those pests. But if you want to talk about pests for common plants, you have what, Dr. Zeti? What pests do we have?
Mealybugs, aphids,
yes,
right? All
yes,
those.
aphids, mealybugs. Oh, so many. Yeah.
Yeah. Okay. All right. Okay. So the next one is from Shakir. Thank you for the presentation.
Thank you,
What
Shaki.
What are your opinions on startup? Are they suitable for your research? If given the opportunity, would Prof. Suraya do a startup for carbon nanotube or carbon dots?
Okay. Okay, thank you for that question. If you had I would say that it would only be, as university researcher, it would only be possible if your university facilitates it. Okay, it would only be possible if your university assists you, if there is an innovation hub, if your university wants to see the researchers commercialize, then it will be possible. And we do. Our commercialization approach is slightly different from the conventional one. The conventional approach for technology is for you to license out the technology to a third party, right? A third party, people from industry, they will come in and they will say, oh, I'm interested in your technology. I'm going to pay UPM the licensing fees for this technology, right? So this is common. This is common. However, UPM wanted a slightly different way of to give opportunity through the startup method. Now, the advantage of a startup method is that the researcher themselves knows more about the product and the potential, and therefore they can assist the entrepreneur. And the idea is that the researcher works together with a unipreneur. A unipreneur could be anybody. It could be a PhD student. It could be a master student, right? Those who have the desire to go into entrepreneurship. And this is what InnoHub allows, facilitates these two parties coming together. And I had that as well. I had a project manager. But when, there will come a time after your market validation studies, there will come a time where you need more grants, right? Or you need people to invest in your startup. Okay, and this is not easy. This is another journey. You've done the research journey. Now you want to do the commercialization journey. It is not easy at all.
But
Did I
it's
answer the
doable.
question? But it's doable. Yes.
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 Okay. Right. I hope to my understanding, I think you have answered the question very
Okay.
clearly. Okay. The
Okay.
next one we have from Dr. Sharifah Nabiha. Hi, Prof. Thank you for the nice talk. May I
Thank
ask,
you.
number one, what is your trajectory predicting on carbon-based materials application in the next years ahead? And secondly, how is the acceptance of stakeholders to this kind of materials base? Thank you.
Okay, if we're talking about carbon, carbon will always be relevant. Carbon will not, I think carbon will always be relevant. And if you're working with carbon, then you will be relevant. Okay, and what is the stakeholders, what was it again? Stakeholders perception, was it?
The acceptance of stakeholders to this kind of material space.
Yeah. Are we talking about what material are we talking about? Are we talking about carbon? Are we talking about carbon nanomaterial? Are we talking about specific carbon nanomaterials? Now that depends. Okay. A lot of people, when they talk about nanomaterials, there's a lot of uncertainty regarding safety aspect, and but with knowledge, this is when knowledge comes in, right? So if you are knowledgeable and you know and you understand, then you can really address these issues. For example, if carbon dots, if we produce them using the conventional method, I would not go through the trouble of trying to apply it for photosynthesis enhancer. I wouldn't. Why? Because of my knowledge about that material. It would not be suitable because it is there's so many processing steps, right? So many steps to make it suitable, making it economical and just not feasible for that particular application. But because of the knowledge of making the carbon dots to be safer, to be more economical, then you can pitch to the stakeholders. All the SDG applications I mentioned just now, if because I know it's possible, then I can pitch to the stakeholder, and then they will understand, and then they will see the potential. Do you see?
Yeah. It's very, very good tips, I think. Yeah. We have to be knowledgeable in our product in order to
Yeah.
defend and justify it, right?
Yes,
Okay.
Dr.
Yeah.
Zeti.
Right. Okay. The next one from Dr. Khalida. What is your opinion on plant extract rather than pure single compound as a starting material of carbon quantum dots?
Mm. I would say it depends what you will be using your carbon quantum dots for. What is the final application? If they are to be used for some, so this is, because the process, sometimes people focus on the process and they are not aware, they think that a green process is good. Everyone wants a green process. However, if the green process is expensive and does not justify the end application, then you will be stuck, right? You will be stuck. So it depends. What will your final application be? At this time, we have found a niche to use carbon dots as a photosynthesis enhancer, right? And this is our technology. This is UPM technology. And it's only possible because of our ability to produce it economically.
Yep. Okay. And the second one, how about the safety on using CQ as spray to the human respiratory system since it is very tiny?
Okay. Right. So the if you were to dry the CQD into powder and you were to inhale, then that's not recommended. But why would you want to would you want to make this powder? Why? This is why I do not make powder. I do not make powder, and I make sure that the nanomaterial produced is produced in liquid. That's number one, so that you do not inhale it. Number
Yeah.
one, right?
Okay.
And then number two is we know the safety limit of releasing it to the consumers. It is very, very low concentration. I would say that, and because it is made out of purified water, you can really, I'm not advising you to, but if you were to drink Havas photosynthesis enhancer, it would be like drinking water. Okay. So because right, so as I mentioned, if you eat satay or you eat barbecue, you know that carbon that you consume, a lot more carbon than contained in a bottle of Havas.
Okay. Right. Okay. Thank you. So the next one, could you please comment on using microwave plasma enhanced decomposition (MPED) process to synthesize carbon quantum dots? Is it feasible?
Yeah, I would say that it would be the way forward to scale up and to make any microwave assisted process has potential. Okay, microwave assisted processes have potential and would be useful to be further studied. It has potential to be it is a scalable technology, and you can pursue it because ourselves we use microwave technology as well, and it really shortens the processing time, right? It shortens the processing time and it enhances yield. So yeah, continue that.
Okay. A word of encouragement there, Dr. Khalida. So, right. So the next one from Dr. Aizat again. What does CQD or biochar or biomass made of to be used for the harvest material?
Havas it is carbon dots, and carbon dots are just that. They are dots of carbon. They are fragments of carbon. They are carbon particles. They are really small carbon particles. They are carbon, basically, just pure carbon. However, they do have functional groups, and they are hydrophilic, right? They are hydrophilic. They disperse well. I mean, like the way that we make it in our technology, they disperse well.
Okay, cool. Yeah. So the next one, I think similar question. What is the source of raw substrate used in the synthesis carbon quantum dots in harvest?
Yeah. We use agro waste. We use biochar as the starting material.
Yeah, that's cool. So biochar, where do you get this biochar as a waste? From what?
Yeah, biochar is commercially available, and we use the one that that is commercialized by UPM.
Oh, I see. Okay, so it's good way, smart way of managing the waste. Yeah. Okay.
Yeah.
All right. So I think that is the end of our questions, and I think we have quite a mix of company based or commercialization based questions as well as the scientific based questions.
Yeah.
So so I think there are many more questions on the scientific part. So maybe we can invite you again sooner or later to share with us the fundamental of science.
If you
interesting.
Yes. If you like to know more about carbon nanomaterials, their synthesis, their characterization, then of course I would be happy to share.
Yeah. I think we have probably have some interest from my research fellows in terms of this area. So yeah, I think will be a good starting point here today. Okay, thank you so much, Prof. Suraya, for your invaluable research experience.
Thank you, Dr. Zeti and INBIOSIS. Really appreciate your time.
So we have
Thank you so much for everyone
Okay,
listening.
we have come to the end of the webinar. So I would like to thank Prof.
You
Suraya
want to take
again.
photo, right?
For the very interesting
Yeah.
subject, and I'm sure it has
Yes.
opened up our view and give you an idea on how you want to bring up your research output to the next level. I also would like to thank all participants for being with us today. Please stay safe and take a very good care of yourself. And before we say goodbye, let us immortalize this session by switching on your video and have our faces captured. Okay, right. So I think we have our organizer to help us snapshot. Okay. All right. So
Thank
today's
you, everyone.
we have a very good turnout. It's 154 on Zoom and about 64 on FB Live. So more than 200. Well done, Prof. Suraya. Thank you.
Thank you.
Oh,
Is
so I
someone
can,
snapping the photo?
yep.
Oh,
I
Dr.
do.
Zeti, okay. Go on.
Yes.
Go ahead.
Okay. So from the organizer, how do we, so hold on, I need to gallery. Okay. Right. Smile.
Thank you.
1, 2, 3. Okay. So we have 9 pages.
Oh,
Yeah, it's a very good turnout. 200 people today. Right. So no more. Okay then.
yay. Thank you so much. Feel free
Okay.
to contact me. Thank you so much. Those who are in the chat saying thank you. Thank you so much, everyone. I really appreciate your time. Thank you so much.
Okay. Thank you, Prof. Thank you all to the organizers
Okay.
and participants.
Bye-bye.
Bye.
Till next time, inshallah, Dr. Zeti. Bye.
Inshallah. Okay, will do.
Assalamualaikum.
Waalaikumsalam.
Bye.
QR code. QR code.